Alright, my name is Benjamin Hupperich, and for my 6-minute talk, I'm going to be talking about the SR-71 Blackbird. So the content of this presentation, I'm going to go over a little bit of background. I'm going to introduce the 3 types of propulsion that are used in this piece of aircraft. I'm going to talk more about the engine design and why it's so complex, and then a little bit about the fuel storage and the fuel at the end. So the predecessor of this plane is the U-2. It's that picture up there. It was too outdated, so the CIA gave a project to Lockheed Martin to create a new surveillance plane, and they started Project Archangel, and the A-12, which is pictured here, is the most recent predecessor to the Blackbird. This is what ended up being turned into the Blackbird, and its main problem, I believe, was fuel storage. But the Blackbird flies at Mach 3.2, which is more than 2,200 miles per hour, at 80,000 feet in the air. It is still the fastest air-breathing manned aircraft ever to be made. And the engineers who made it actually used slide rules because they didn't have calculators. So that's another interesting thing about it. So the 3 types of engines that are used in this plane are ramjet, turbojet, and an afterburner. The ramjet is actually a static engine. It uses ram pressure, which is created by velocity. So the plane has to be moving at Mach 1 to be pushing air fast enough through a diffuser that compresses the air. And then it's ignited in a combustion chamber similar to any engine you know. And then the turbojet is what we have in the lab. It's just a compressor that's driven by a turbine, and the turbine is driven by the exhaust gases. And an afterburner, in its simplest form, is something you stick onto the end of the engine to suck in the excess oxygen. They spray more fuel and ignite it in there. So the Pratt & Whitney J58 is the engine of the Blackbird. That's a picture of just the turbojet on the bottom, but this plane uses a turbojet stuffed inside of a ramjet. So I'm going to just be referencing one of these pictures. It just shows how this engine changes because it is dynamic. So air comes in at a ramjet spike, it flows through into the turbojet, which is this big gray portion, and then there's an afterburner at the end as well. This engine evolves when it flies through the air because since you need to be going at Mach 1 for the ramjet to be active, you can't really be running a ramjet without running the velocity, so the ramjet moves backwards as you move faster through the air. And as you can see, the inlet of the plane is flared, so as you move backwards, that inlet area decreases, causing a greater pressure ratio. And you can also see that they make sure to point out different types of airflow throughout this plane because the airflow changes. As you get faster, that turbojet gets less and less efficient, so you actually want to be using it less. And I will talk about that now. So the first piece of airflow control that I'm going to be talking about is the center body bleed. If you look at the top picture, it says it about in the middle. Air flows in through the ambient air up through the ramjet spike, and this is to provide extra air supply to the plane when it's not moving very fast. But as the plane speeds up, that airflow actually reverses. And the reason for that is the ramjet has slits in it that take in the boundary layer, which is just a film of slow-moving air that develops as you move faster, and it spits out that boundary layer to the ambient air. It's bad air, you don't want it. This is to make more room for better air flowing in through the inlet. The next piece of airflow is the forward bypass. It's on the bottom left at the top picture. As you can see, the forward bypass in the beginning, its job is to suck in. This is just extra airflow when you're not moving quickly. And its job at the end, as the plane moves faster, is to position the shock correctly, which I will also talk about in a second. But this vent is triggered by a pressure sensor, so it opens automatically. It's the pilot's job to balance multiple types of vents in this plane to make sure it gets started correctly, which I'll also be talking about later. And then there are multiple different types of venting. As you can see, they have suck-in doors and then tertiary doors. These vents' job is to supply air to an outer duct that cools the outside of the plane and supply the afterburner with extra oxygen as needed. And then for the shock control, the most important part of this plane is that forward bypass door. So as the spike moves backwards, it's not only decreasing that inlet area to be pressurized more, it is also positioning the shock correctly. So a shock is a phenomenon when you have a fluid moving supersonic. It changes properties like instantaneously. So I have a graph here When you have a shock wave, when the fluid hits it, you can see in the middle graph the Mach number drops drastically and the pressure ratio increases for ambient pressure. And then on the left is a picture of actually what the shocks look like. So there are two shocks in this plane. There's a leading shock at the front of the spike, and there's a normal shock inside of the ramjet. It's the white line that ends inside the engine. And if you look at the picture at the top, it lines up about correctly with that vent. So the vent's job is to detect when the shock hits that position. It opens up and allows air to flow out, creating less pressure. And once the shock is set, it should look like this picture. It's called a started inlet. If the shock is not properly set, the engine starts spitting air out, and it looks like the left picture, which is an unstarted inlet. And then at the end here, to talk about the fuel storage. So the clever way they had to store fuel, one of their problems when creating this plane was with the cross-sectional area. So they decided to store the fuel in the skin of the plane. So it was made of these titanium plates that are finned like a heat sink, and the fuel flows between these plates throughout the entire plane. This is done to maximize the amount of storage and to cool off the plane. As you can see, this plane is 25 tons dry weight, so when it's fueled, it's 61 tons. So this plane holds about 80,000 pounds of fuel. This fuel storage, even though I think it is a really clever idea, it's actually kind of the reason the plane got decommissioned. You can imagine that sealant needs to be applied between these plates, and sealant doesn't really hold up at 500 degrees. So every time the plane landed, it needed about a month's worth of maintenance in order to be put back into commission. So yeah, that is about all I have.
Any questions? Yeah, just one. I see you talk about the ramjets. Like, why do you think they did not use a scramjet for this purpose? Or do you know what this?
It's like a supersonic ramjet.
Yeah. So like, why is it not used?
I do know that like 80% of the thrust generated at top speed is actually just for air. So like combustion actually doesn't play a big part in thrusting this plane forward. This plane could only run, I think, ramjets can run at Mach 5, right? And this plane only runs at Mach 3.2.
I think ramjets supposed to be able to work once the speed is above supersonic speed.
But I think their maximum speeds.
The maximum speed for this aircraft now is 3.2, isn't it? That's Mach 3.2.
Mm-hmm.
Yeah. Well, if you add up supersonic ramjets, you will see that like it's still in the development stage. It's not yet being used. It simply means you are trying to burn the air at supersonic speed. That's what this ramjet actually does, is that it kind of decreases the speed, because for combustion to happen, the air needs to be very, very slow. It needs to be slow enough. So the ramjet's purpose is just to decrease the speed a little bit and then allow burning to take place. But if you can actually burn at very, very high speed, it will actually make more sense. But then they are still working on it, as the different research are still looking at making that kind of possible. Well, this is a good one.